Hello, everyone. So I am Joshua Brown from Imperial College. It's worth saying now right up at the front, I'm with Imperial now, but a lot of the work you're going to see came from my PhD at Queen Mary University of London, and a little bit as well at York University in Canada. So watch out for that. I'm going to be talking about using particle jamming, which is an effect that we borrow from soft robotics, to create softness changing and ultimately multimodal haptic interfaces. So I start all of my presentations by asking, what is particle jamming? And I guess I'll have made it as a researcher when I don't have to anymore. But really, particle jamming is an effect where we can create soft structures with a granular fluid. So something like seeds or sand or coffee grounds are very popular. And they're very soft and very malleable and very loose in their unjammed state. And then in some way we compress them together, and that's normally done with a vacuum. And then they brace against each other and you get this hard structure. And in haptics, of course, that means you can create haptic interfaces that become harder or softer in the hand. This has a few different applications. In tactile displays, we've got an example here from Alison Okamura's lab at Stanford, where they've created a 2D array of particle jamming cells to create a hardness changing surface. And I think the idea is that they use it to train clinicians in palpation. So if you're looking for a hard lump on a patient, you can create this hard nodule in your tactile display, and then your medical students come in and try to find it. On the more kinesthetic side of things, you can also use particle jamming in exogloves, exosuits. If you want to be able to control the movement of a person's joints, you can put a jamming pouch along maybe their finger in the example here, and then you can harden it and lock that joint in place, perhaps when they pick up an object in VR. I'm really interested in particle jamming for another reason. It's got a really lovely property where in the implementation of a particle jamming device, there's a lot we don't care about. We don't care what the particles are made from particularly. We can embed other technology inside the jamming device, inside the fluid. And we can also make parts of the jamming container out of different materials, different pieces of equipment. So we can put maybe temperature changing plates or other technology around the jamming fluid. And that's something that you've already been introduced to in Amy's presentation earlier this morning. I want to take a case study of this, the combination of softness change and vibration, which is a topic that I looked at in my PhD with Ildar Fakatanov, who's in the audience. And it's really quite a simple idea. You take a particle jamming based tactile display. So you have your box of quinoa seeds in this case. And if you evacuate the air, it becomes hard, the particles jam together and you get that hard surface. But if you also embed a vibrating motor inside that, and we've got an eccentric rotating mass motor here, then you can also get the particles to vibrate, and that vibration will propagate up to the tactile surface that your user can then feel. So you can see in the video here, because it's made of silicone and sealed, you can also inflate it. We get some shape change. But then you can see when you suck the air out in a second, it's going to become a very solid, very rigid display. And then when you start to release the air pressure, the particles start to move around again, and you get that vibration effect. And the first thing we needed to do with this technology once we designed it was to characterize it and see how do these different tactile modalities interfere with each other in an engineering sense. So to do that, we were really interested in the vibration propagation. So we just attached a small accelerometer to the top of the silicone surface to see what the vibrations did when we jammed the particles. And to cut a long story short, when you change the vacuum pressure, so when you jam the particles together, the vibration amplitude actually decreases. I think that's because the particles are actually damping the vibration motor and kind of locking it in place inside the device. But what's really interesting, if you look at the frequency spectrum here, there's actually not all that much difference in frequency when you are affecting the particle jamming change. And that means that when you have your so-called high definition vibrotactile effects, your clicks, your pops, your chirps, you can still create those in this kind of multimodal interface. So you retain a lot of the vibration properties that we actually care about. After we developed the technology, we wanted to turn it into interactive devices that people can actually use. And there were three things to really look at. First of all, interaction. How do you sensorize these types of devices? How do you make them more ergonomic? That means a change in form factor. Is that going to affect the properties of your device at all? And finally, control. If you do have this change in amplitude, for example, how do you make sure that the effects you're delivering to your user are consistent in an interactive multimodal device? So the first example we came up with was a soft joystick. You can see here we have a 3D printed silicone grip, which is basically your joystick handle or shaft. We then fill that with the quinoa seeds, and we've replaced the vibrating motor here with two voice coil motors from Actronica, which give you really high definition vibration effects, and that'll become useful later. And then we just seal it and we connect it to an air port so that we can evacuate the air and affect the particle jamming change. So here's a schematic view of the same thing. You can see we've got the two voice coil motors. We have two of them, to make sure that you can feel the vibrations consistently up the entire length of the joystick shaft, but also so that you can actually change, they're controlled independently. So you can actually have different effects at the top and bottom. That might be interesting for psychophysical research. So I mentioned the question earlier, does form factor affect the performance of a jamming-based device? It's fairly obvious, I suppose, that if you change the hardness of a device, then the vibrations are going to change in amplitude. But we're really interested in the frequency response. If you change the hardness of your haptic interface, can you still transmit vibrations through it? If you see in this frequency spectrum here, we have, this is in the soft state, and then in the hard state, really very little change. So there's a little bit of resonance because of the length of the joystick handle. But for the most part, we're quite pleased that changing the form factor of this device doesn't actually change how it behaves from a mechanical standpoint. So no, form factor doesn't affect performance. We also designed this multimodal haptic touchpad. And this is a little bit interesting. It's the same kind of design as you've seen before. We have the box filled with quinoa seeds, and then another much larger voice coil motor inside. But this is on a force sensing base. So we've got two load cells, one on the left, one on the right. And what that means is you can sense the fingertip position from left to right, but also the magnitude of force that your user is pressing down with. So that means you've got two modes of input interaction, and then two modes of output as well, your hardness and your vibration. So the first thing we wanted to do with this was look at the perception of these multimodal effects and how they could be used to perhaps trick a user. So we're looking at using tactile cues, these multimodal tactile cues, to enhance the sensation of virtual objects. So feeling virtual objects through haptics is really quite important, but it's also an open problem. You can see in the graph on the right here, you have your ideal haptic wall is going to be very rigid. Basically, you touch a hard surface, it's not going to give at all. It's very hard, it's very rigid, and it doesn't move. And that's very difficult. That's a very difficult effect to produce with a haptic robot, because you need a very fast, very high force response, but then you need to be able to turn it off as soon as your user moves away from the wall boundary. And what you very often end up with conventional haptic robots, particularly low-cost haptic robots, is this much spongier effect where the force builds up over time as you move inside the wall. And in a session like this, where we're talking about soft objects, you might think, well, that's quite convenient. We can render foam, silicone, gel. But actually, if you want to produce a hard surface, then that's a really, really difficult effect to create. So what we're interested in is, can we use tactile effects at the wall boundary to create the illusion that you are touching a hard surface? So here we have a 1 degree of freedom torque feedback robot. That's the HRX1 from Human Robotics. Talk to me or Ildar about that after the presentation. It's our startup. And then we've attached the soft haptic joystick to it. So you can see here, as you're moving into the wall boundary, it becomes very hard in the hand, very rigid. And then when you're outside the wall, it's much softer, more flexible. And we can also make it vibrate at the wall boundary. So we set up a study with 12 participants to look at the effects of these different sensations. So we have walls rendered with just stiffness, where you're moving the robot handle and you get the torque feedback inside the wall. We have the combination of stiffness and hardness, where the joystick becomes hard in your hand at the wall boundary. Vibration, and that's a 200 hertz vibration, because there are some known effects of vibration creating phantom muscle sensation. So we wanted to avoid those at the lower end of the vibration range. And then the combination of hardness and vibration on the wall edge as well. And what we're really looking for here is the participant to compare two walls and tell us which was the hardest, the one rendered with just stiffness or the one rendered with one of these tactile cues. And we did this with something called an adaptive staircase protocol. So for those of you who aren't familiar with psychophysical research, you basically take your two stimuli at the furthest differential between them. So we have our baseline wall, and then we have a much stiffer wall. And then you gradually bring them together, and each step ask the user which felt stronger in our case. Was it the wall that was less stiff but had the tactile effect, or the wall that was stiffer but didn't have any tactile feedback? And eventually you get to this convergence point where the user can't actually tell any difference. And if that point is a long way away from your baseline, then there is an effect with this tactile cue, and that's your just noticeable difference. So this isn't published yet, we're still analyzing it. But to take the example of one participant who was representative, you can see that in all of the cases there is a gap between the tactile wall and the pure torque feedback wall. And you can see that in a lot of cases, the user really did get quite a long way through the experiment before they could tell a difference. It's also worth pointing out here that we did both an increasing and a decreasing case to make sure that we covered a full range of stiffnesses that the robot could produce. So the first thing we wanted to do was to compare different cues. And what's really interesting from the results that we've got so far is that there's actually a really stark difference between users as to which cues they felt were more effective in rendering a strong wall. So you can see here participant 5 really liked the hardness effect, whereas participant 9 here got a much stronger sensation from the combined hardness and vibration. So actually that's a really strong argument for producing multimodal haptic interfaces. People respond differently to different physical sensations. And the more effects you have in your haptic interface, then the more different users and different use cases you can accommodate. And we're still looking at this data and working out psychometric functions and things, but we're planning to submit this to Transactions on Mechatronics later this year. The other application area I want to talk to you about is teleoperation, and I did this work at York University with Michael and Heather Jenkin. So teleoperating underwater robots is a very challenging task. Underwater environments are often poorly lit, they can be quite dynamic, and they very often have complex 3D geometry. So you can see here some imagery from a dive from Osama Khatib's group, again at Stanford, where they're operating inside a wreck underwater. And there are really tight, confined spaces, no lighting, that are quite difficult to operate in. And as we saw even last year, when underwater operations go wrong, there can be really tragic consequences. A well-understood hazard in underwater operations, especially with robots, is cross currents. These are invisible columns of water that will move your robot off its predetermined course. And very often, if you're operating in open water, there's no visual cue that you're about to experience this perturbation. And a recent report from the UK National Oceanography Centre said that these currents can reach 20 miles an hour, which is quite a strong perturbation for your robot if it's not expecting it. So we set up an experiment to see whether multimodal haptic feedback can be useful in keeping an operator apprised of the environment their robot is operating in and any unexpected changes in state. So we have an experiment here. We got 8 participants where we have an underwater robot, in this case, the Blue ROV2 from Blue Robotics. And it's going to travel 4 meters to a floating red ball under the water. And in the middle of that 4 meter distance, we've set up a fixed thruster which is generating a cross current in the robot's path. And it's worth saying we didn't set this up as a learning study, but we also didn't give the users a training phase. So what we did was we split the study into two parts. We gave them each condition, still water, cross current, and cross current with haptic feedback, 5 times each in a kind of a learning phase. And then we went back and we did the whole experiment with them again, to see whether once they had some experience of operating the robot and once they understood the scenario a bit better, whether their performance improved with or without the haptic feedback. And this was quite a data-rich experiment. So we're looking at cognitive workload with NASA TLX. We're looking at various performance metrics, accuracy, the time they took, the drift due to the cross current, and their overall path length, their efficiency, and a few proxy metrics for confidence as well. And I'm not going to have time to go through all of these results. But the interface we gave them was the touchpad, which you might be thinking isn't a particularly obvious approach to teleoperating a robot. Why wouldn't you use a joystick? But we wanted these 2 inputs and 2 outputs. So the user was able to steer the robot by moving their finger left or right on the touchpad and control the speed by pressing down with more or less force. And it's got that force sensing base. And then in output, we used the vibration to indicate a sideways movement, often due to the cross current. And then also the hardness indicated their distance to the target. So were they able to pull up and stop without crashing into it? So here you can see they got some visual feedback as well. And then this is one of our divers demonstrating the experiment for us. So you can see he's using the touchpad to control the robot. And here it's just been moved off course by the cross current. So he's coming in at a bit of an angle, but he's still able to find that target. And here's the underwater view now. You can see we're coming up on the thruster, which may or may not have a cross current, but I can tell you there was a cross current in this trial. So we're staying nice and steady on target. And then all of a sudden you see the robot start to move off course. And that's fine, that's visible in a study like this, but in open water, you'd have a problem. So I'm going to fly through the results quickly because I've got some other stuff I want to talk about. But the cognitive load, we can see that there's an improvement in this familiarization phase, but not once participants were already familiar and already experienced with using the robot. And we get a similar story for accuracy as well. There's a statistically significant improvement at the beginning of the study where participants are novices, but not later on when they already know what they're doing. All of this stuff has been quite cool and quite interesting. But inside a lot of soft haptics research, we have a little bit of a dark secret, which is this thing. Whenever you're working with pneumatic or vacuum operated devices, you have to have a big pump, regulator, controller, power supply. And this is actually quite an inefficient system. You can see here in this example, the little tactile display is only 10% of the system volume because you've got the big pump has to be connected to a wall outlet. It's not portable, it's not quiet, it's not efficient. And really, after I did all of this work, I set myself a challenge. If I want to carry on using this technology, can we make it affordable so that other people can use it too? Can we make it lightweight to be used in wearables and portable devices? Can it be quiet so we don't have to play white noise to all our participants? And can it be power efficient? Because that's just good engineering and we don't want to be plugged into a wall outlet. So my work now in a postdoc, in collaboration with Professor Fernando Bello, whose group I'm in, Dr. Lynette Jones at MIT, and of course Amy, who's up at the back there, is looking at using particle jamming to create a new generation of soft multimodal tactile displays. So the sensations we've set ourselves, of course, are softness, but we're also interested in vibration, I've talked a lot about already, temperature, shape change, and friction. So as I mentioned, the state of the art for particle jamming is vacuum actuation. This is where you evacuate the air from your particle jamming device. But of course, you have to have this rather nasty pneumatic system to go along with it. And the first stage of this work, we wanted to re-engineer the particle jamming foundation so that we can create a device with all of those characteristics I mentioned before: affordable, lightweight, power efficient. So the first approach came from an observation in all of this earlier work, where if a person is actually pressing on the particle jamming device, we found that they actuated the particles themselves. So what we've produced here is a mechanical particle jamming device with an inelastic container. So this is just cotton fabric. And then we have an eccentric cam that pushes the particles up, bracing against their own container. And what that means is you can jam the particles with just an electric motor, no vacuum, no silicone, no regulators. We can do a similar thing by twisting the fabric as well. You twist the fabric up, the particles are compressed from all sides. And this again affects the jamming effect, creating a hard tactile surface. And the other approach we're looking at is magnetism. I mentioned that we don't care what the particles are made of, so if we make them magnetic, why can't we use an electromagnet to attract them to the bottom of the container and then jam that way? So we built prototypes of these devices. I showed off the mechanical ones at Haptics Symposium in April. And then the magnetic one is actually in review for Frontiers in Robotics and AI. We've actually just been accepted by one reviewer. So if reviewer 2 is out there, please have a look at the revisions. They're really good, and we want to get this work out there. To evaluate these devices, we looked at the shore hardness, which is quite a popular way of assessing material hardness and softness. We just used a shore hardness probe to probe the surface at different points as we were actuating them. 9 points so that we can look at the uniformity of the hardness change as well. And you can see here, actually quite surprising, the constriction approach gave us the hardest surface. There is a line at the top, which is the vacuum effect without a regulator. That's just a fine vacuum. But actually you can see in the purple line, when you actually put that regulator in series, it gives you a limit to the vacuum pressure you can create. And that means that actually the vacuum effect doesn't give you as hard a surface as some of these mechanical devices, which can really torque up and twist your material. We looked at response time as well. And again, because of that regulator, the vacuum powered device is over 3 times slower than the mechanical devices. So this is a really, really strong argument for not using vacuums to actuate hardness changing displays as if you needed one. So there are really 2 directions we want to take this work in. My main project is medical simulation, and we're really interested in this as a way of training doctors to palpate and examine patients who, of course, are soft, fleshy individuals. So in the work you've already heard about with Amy at Seoul National University, we're investigating ways of changing the size and shape of soft haptic interfaces based on particle jamming to change their hardness as well. And then with Lynette Jones at MIT, we're also investigating temperature change in various ways. We also want to release this work as an open hardware project. Due to our funding, there's a little bit of discussion around that, but we're looking at a Creative Commons non-commercial license. And you can see this example is fully 3D printed, apart from a motor and the spring. So all it is a sleeve of fabric filled with quinoa seeds, and when you twist it from one end, you basically wring it out and you compress the particles along that shaft. Well, thank you for listening, and I'll take any questions.
Thank you very much. Very interesting. Is there any question in the audience? Yes.
Yeah, thanks for your talk. I was really interested in your alternative mechanisms for the particle jamming. And are there any like downsides? Like I can imagine a vacuum's nice because you get nice conformal packing, and then maybe your quinoa seeds are really like, right, not round. So then maybe if you use some of your other mechanisms, you have like these soft patches because it didn't quite pack in some spots. Did you see any kind of lack of uniformity through your other mechanisms?
I'm glad you asked. Yes, we did see some lack of uniformity, so I didn't have time to put this in the presentation. But definitely with the vacuum, and actually the compression prototypes were quite uniform because you have that solid plate lifting up over the whole of the device. But you can see with the magnetic field and with the constrictive device, where you're twisting from the outside, you do get some loss of uniformity in your device, which actually for some workloads like medicine, where you're trying to create hard nodules, can be useful. In other cases where you're trying to create a uniform hardness change, is less desirable. So it's about using the right tool for the job.
Thank you.
Thanks for the talk. I'm wondering about the size of the particle and their internal friction. Is there any preference material or direction you would better what you tried?
So this isn't something I've had an opportunity to experiment with myself. I have had some questions in the past about particle size and how that affects particularly the hardness change. My hypothesis, I suppose, if I were to be able to do this experiment, would be that smaller particles would jam together and brace a lot better because you could have more contact points in a given volume. But then actually for transferring the vibrations, you would want larger particles because you then need more interfaces for the vibrations to actually propagate through to get to your user at the end.
Thanks.
Anyone else? So I have one question. So I think on slide 7 or something, but you don't have to show it. You see the vibration and you see the particle getting trapped or getting stopped. Yeah, in this video. And I don't know, when you look at it, it looks like these are modes of vibration of these grains, right? And then you just freeze the mode of vibration. I was wondering if you run some sort of analysis or at least like FEM of the vibration of the grains themselves, if they go like, Caldney figures or something like this.
Yes, so all of these experiments were done in static states. So we would change the hardness of the device and then let it settle and then take our measurements. We didn't do any dynamic experiments.
Right.
The video is slightly misleading because, of course, it's quite difficult to video vibrations. You can see the particles moving, but then when you jam them, they're still vibrating just as a solid mass.
Yeah, but it looks like the surface has a certain, sinusoidal shape.
The surface, that's not to do with the vibration. That's to do with the compression of the silicone causing it to expand.
Okay.
So the silicone patch there is actually slightly oversized because you compress it at the edges to seal the container.
So why does it get pulled somewhere and then pushed the other way? I don't get it.
So that's the air pressure change. When you inflate it, we were doing some inflation here as well to show the shape changing properties. So that's where it inflates. And then when you evacuate the air, it sucks back down. But it won't sit flat because, of course, it's slightly large.